In facilities design, we are going to talk about the warehouse space, the load and unload docks and trucks, the packaging, statics and material handling, the rooms and dimensions, and the parking lots. For the warehouse space, we're going to talk about the racks, the storage boxes, and the doors. These details matter to us because it helps us understand what kind of facility we are dealing with. For the racks, we're using 3 different types of racks: the drive-in racks, the pallet floor racks, the recycled wood pallets. We're using the drive-in racks for storing the bigger parts that cannot be carried around the facility. And on the right you can see the pallet floor racks and the recycled wood pallets. For the recycled wood pallets, we're going to use them to be 48 by 40 inches, and their height is going to vary from 5 to 7 inches from the floor to the top of the deck. And we're going to use from 20 to 25 empty pallets in every standard stack. For the boxes, we're going to use the triple wall boxes that are used for heavy duty, and they're going to be 30 inches in length, width, and height. And to calculate the number of boxes we're using, we're going to divide the inner length of the truck divided by the width of each box, and it's going to be 636 inches divided by 30, so we're going to have 21 boxes in each lane inside the shipping truck. For the doors, we're going to use 4 different types of doors: the GRP swing doors, the S-type, and the R-type, the high-speed doors for the forklifts and the other smaller transportations that need to access the facility, the Novus Print doors, the smaller automatic doors that are needed for the people who are traveling in the facility with parts, and the rolling shutters, the garage doors that are needed for the load and unload docks. For the load and unload docks and trucks, we're going to use open docks with the sawtooth docks. And for the trucks, we are going to use the container trucks because we have big products that need the bigger kind of trucks. And the truck dimension is going to be 53 feet by 9 feet by 10. And the inside dimension is going to be 109 inches for the inside width, 636 inches for the inside length, and 120 inches for the height. Now for the packaging, statics, and material handling, which we try to calculate how many boxes we have, and how many lanes, and how many levels in each kind of truck. So we're going to have 21 boxes in 30 lanes and 3 levels. So we're going to have 189 boxes in each shipping truck. How many forklifts in the facility? We're going to have from 4 to 5 forklifts. Rooms and dimensions. In the facility, we're going to have different kind of rooms. We're going to have a factory, which is going to be 400 by 132. We're going to have offices for the staff. We're going to have restrooms, water closets, cafeteria, conference room, management offices, which are going to be different from the regular offices because they're going to be bigger. We're going to have 2 storage areas, 1 storage area for the raw materials and 1 storage area for the finished products and goods. We're also going to have front desk and main entrance. We're going to have locker rooms. Now for the parking lots, we're going with an open parking lots, not the enclosed ones. And we're going to have a parking space for every 1.25 employee at one extreme and 1 parking space for every 3 employees at the other extreme. We're also going to have from 2 to 5 handicapped parking spaces per 100 parking spaces. And the parking lot is going to be in the following dimensions. The following is a semi-model of how our facility would look like. It's just a basic facility layout. We would have the load and unload docks and trucks. We also have forklifts over here. And as you can see, the facility have different workstations. And of course, in the front of the facility, we have the parking lots, the open parking lots with the 90-degree angles. We use Semio to have the layout of the facility, and this is in 3D view. Here you can see how it would look like in 2D view.
For the business plan, we're going to start with our objectives first. Our company is planning to work with the Jacobsen as our primary customer. We intend to produce 1,000 diesel engines every month, making a profit of 20% for every $1 million. First, we start with our fixed cost. Cost of renting the building will be of $65,961 every month. That would equal $791,529 per year. We are planning on using 10 trucks for shipment, and that would come to $350,000. Triple wall boxes will be used inside the facilities for storage and movement, and that would equal $68,040. The forklifts that we plan to use would come to a total of $4,492. For our variable costs, we include our employee wages and engine parts. We would have a total of 94 workers earning $26 per hour. This would equal $391,040 per month. That would come to $4,692,480 every year, just in employee wages. Our engine parts would cost $4,710,000 every month, which would equal $56,520,000 per year to build the engine. Our revenues would be $2,120,000 for every 1,000 engines sold. This would be for every month. For every year, it would equal $25,440,000 on the first year, and we would have an increment of 20% on year 2, and so on, due to the taxes and increments for selling the engine. This would mean that we would have to sell our engine for $6,830 per unit or per engine, which would come to $6,830,000 for 1,000 engines sold every month. Our profits would then be $25,440,000 per year with an increasing rate. And after taxes, we assume 20% of taxes on due to research. That's the average amount of tax for this type of industries. We would have a profit of $20,352,000 every year, with a steady increase on the following years. With this, we can see our break-even analysis. We see that on year 14, around year 14, year 15, we will have a break-even point, having the cost of $241,582,076 and a revenue of $261,303,085.9. That year we would have a profit of $19,721,010. And this would be it for the business plan.
Hi, my name is Jiwon Kim, and I'll be talking about the manufacturing of our project. So here are the parts list. We originally had more than 600 parts, and these are the components of the car, but we thought it will take too much work to list all 600 parts and do logistics and business for each of the parts. We just decided to do just the overall components of the parts list. So we have 37 parts. Some of them were repeated, but those represent will be representing like two different parts for one component, such as ID number 26 and 27 starters. Those are two different starters, but later, if you look at the precedence diagram, it will be combined together, and then go to and work on the next component. So before we go to the precedence diagram, here are the list of which activity comes first. So this is what it means, and this is our pretty much the precedence diagram / our Sumio model. So yeah, it goes from source 1 to gasket. Start from gasket to accessory parts, and whenever the repeated parts comes up, it will be worked in two we'll divide into two lines and then combine together, and then go to the next components, and then here too will be two separating and then combined later here also. And for this part, for this portion of the precedence diagram, so the reverse tank are two separate parts, and also intake exhaust manifolds also are two separate. So what I did was those two separates here and follow with the next part, and the second intake component will be combined right here, and then move on to the next components, which are the turbo parts, turbocharging, turbo oil pipe, and the turbo cooler. And then these three will be combined here, and then finally the accessory parts. The product flow line. So our goal is to produce 1,000 engines per month, and we assume that there are 20 days in a month. And if we did the calculation, we have to make at least 50 engines per day. And every day we only have 48 minutes. So if we were to do the calculation, then ideally we had to make one engine every 9.6 minutes. So here's our Sumio model for our manufacturing. So as I mentioned before, we have to make one engine for every 9.6 minutes. So for source 1, I assumed that every 9.6 minutes we're starting to make a new engine, and since we didn't have information about how many time it would take for each component, I just assumed that for every component it would take 9.6 minutes to make to process. So here, if I run the model and stop, the result will come out to be 50 numbers created.